Hello everyone, welcome back. If you've been following along, you know that we've already covered some crucial foundational topics for machine learning projects. In our previous videos, we explored how to properly arrange your files for a machine learning model, set up Python's virtual environments, work with Anaconda, and get comfortable using Pandas for data manipulation. These are all essential skills that lay the groundwork for any data science or machine learning project. Today we're going to build on that foundation by diving into a practical machine learning project focused on predicting heart disease. In this video, we'll take you through the process of loading the data, exploring its structure, and visualizing important patterns. These steps are vital in understanding the data before moving on to more advanced tasks like preprocessing and model building. Let's get started by importing the necessary libraries. In any machine learning project, you'll frequently work with NumPy and Pandas. NumPy is essential for numerical operations, especially when you're dealing with large arrays and matrices. Pandas, on the other hand, is a powerful tool for data manipulation and analysis. It provides data structures like data frames that make handling and analyzing data more intuitive. By importing these libraries, we're setting up the environment we'll need to work with our dataset effectively. Now that we've imported our libraries, the next step is to load our dataset. We're working with a CSV file named heart.csv that contains data related to heart disease. Here I'm using the read_CSV function from Pandas to load the dataset into a data frame called heart. The file path provided /dataset/heart.csv is a relative path. Let's break down what this path means. The Jupyter notebook and the dataset are in different folders so that the double dots at the beginning of the path indicate that we want to move up one directory level from our current working directory. After moving up one level, the dataset directory is accessed, and within that directory we find the heart.csv file. Using relative paths like this is common in projects where you want your code to be more portable. It allows the script to find the dataset as long as the relative structure of your directories is maintained, regardless of where the script is actually run from. Just ensure your dataset is correctly placed in the specified directory relative to your script, or else the path will not work. Once we've had a first look at the data, it's important to understand its overall structure. This includes knowing the types of data we're working with, how many entries we have, and whether there are any missing values. The info method in Pandas provides a concise summary of the data frame. Here's what it tells us about our heart disease dataset. The dataset has 1025 entries, with each entry representing a different patient. There are 14 columns in total, each corresponding to a specific feature or attribute. Most of the columns are of the data type int64, meaning they contain integer values. However, the all peak column, which measures Saint depression, is of type float64, indicating it contains decimal values. Importantly, there are no missing values as indicated by the non-null count being equal to the total number of entries 1025 for each column. This information is crucial because it helps us identify if any data cleaning or preprocessing will be needed later on. For instance, if you notice a lot of missing values or incorrect data types, you will need to address these issues before moving forward. Next, let's focus on understanding our target variable. The target variable is what we're trying to predict in this case, whether or not a patient has heart disease. Here I'm using Seaborn, a statistical data visualization library, along with Matplotlib to create a count plot. The value underscore counts function gives us the distribution of the target variable, and the count plot function visualizes this distribution as a bar chart. This is a simple yet powerful way to see how balanced or imbalanced our classes are. Interestingly, when we visualize the data, we find that the count of normal people and people with heart disease in this dataset is quite balanced, with both close to 500. This is a good sign, as it suggests that our model will have enough data to learn from both levels, potentially leading to more accurate predictions. This code creates histograms for all the features in the dataset. By setting bins 50, we define the number of intervals or bins for each histogram, which provides a detailed view of the distribution of values. The fixed size parameter allows us to control the size of the entire plot, making it easier to see all the histograms in one go. From the histograms, we can observe that most of the features are categorical, except for a few continuous ones like age, stress peak, thalak, and all peak. Everything looks fairly normal, with most of the features showing expected distributions until we examine the old peak feature. Here we notice a sudden peak at the value 0, which is unusual and worth investigating further. Such anomalies can sometimes indicate important patterns or issues in the data that we need to address during preprocessing. Finally, let's delve into the relationships between our features by creating a correlation heat map. Understanding these correlations can give us valuable insights into how different features interact with each other. We start by calculating the correlation matrix with the corr method. This matrix shows how much each feature is related to every other feature, with values ranging from -1 to 1. A value close to 1 indicates a strong positive correlation, meaning as one feature increases, the other tends to increase as well. A value close to -1 indicates a strong negative correlation, meaning as one feature increases, the other tends to decrease. The heat map visualizes this correlation matrix, with the not true parameter adding the correlation values directly onto the heat map, making it easier to interpret. The CMAP parameter sets the color palette for the heat map, and fixed size again controls the size of the plot. Upon examining the correlation heat map, we found some interesting patterns. CP chest pain type and thallic maximum heart rate show a positive correlation with the target, with scores of 0.43 and 0.42, respectively. This suggests that patients experiencing certain types of chest pain or achieving a higher maximum heart rate might be more likely to have heart disease. On the other hand, old peak and exercise-induced angina have the most negative correlations with the target, with scores of minus 0.44 each. This indicates that higher SIN depression and the presence of exercise-induced angina are associated with a lower likelihood of heart disease in this dataset. Thalassemia and a number of major vessels also have negative correlations with the target, with scores of minus 0.34 and minus 0.38, respectively. This suggests that these features are associated with a lower probability of heart disease in this dataset. Additionally, sex has a negative correlation of minus 0.28 with the target, indicating that in this dataset, females have a slightly higher chance of having heart disease compared to males. However, remember that this correlation is specific to this dataset and may not reflect real-life scenarios. These insights are crucial because they help us identify which features are most relevant for predicting heart disease. Features with higher absolute correlation values, positive or negative with the target variable, are often more informative and might be given more weight during the model building process. In this video, we've covered the essential first steps of a machine learning project: loading and understanding the data, visualizing key aspects, and identifying important patterns through correlation analysis. These steps are the foundation for any further data processing, feature engineering, and model development. We found that most features in our dataset are categorical, with a few continuous features like age, chest peak, stroll, thallic, and old peak. Interestingly, the old peak feature showed an unexpected peak at the value 0, which might require further investigation during data pre-processing. We also uncovered valuable correlations between features and the target variable, providing insights that will guide us in selecting the most relevant features for our model. Remember, while these correlations are useful for understanding this dataset, they should not be directly applied to real-world scenarios without further validation. In the next video, we'll dive into data pre-processing, where we'll handle potential issues such as outliers, scaling, and encoding categorical variables. This step is crucial for preparing our data for effective machine learning model training. So make sure to stay tuned, and we will discuss further in the next video.